even I can say any groundbreaking way to pinpoint on things like whether one should consider temperature and thermal effects, like the effects of thermodynamics into considerations of quantum mechanical calculations. So Unruh effect was the first thing, and that even not in quantum mechanics, in quantum field theory, that we first got to see the effects of thermodynamics and other thermal phenomena in quantum mechanics. And they were first described by Stephen Fooling in 1973, Paul Davies in 1975. Though he was a mathematician, he contributed the mathematics to the system, and William Unruh in 1976. Now, why have I chosen this topic for talking today? It has an interesting background. William Unruh, he has published almost 1,400 articles in his lifetime. He's
Mr. Mandas, sorry to interrupt. The slideshow is not visible. The PowerPoint screen is visible. You need to share the slideshow screen.
1 second.
Yes, your slides are visible. You can continue.
Yeah, sorry, there was a glitch. Extremely sorry. So what I was talking about William Unruh, no? Hello.
Yes, yes.
Yeah. So William Unruh published almost 1,400 articles in his lifetime. He is still alive, so we will expect many more papers from him, I guess. So, and 1,400 is a hoping paper in theoretical physics. Like Einstein in his whole lifetime published only around 350 to 400 papers for reference to understand the amount of research output that William Unruh produced. But why then do we not know his name that much, or he is not as famous? Because almost 90%, and it's quite a record, that almost 90% of his works were all wrong. Like they were proved to be wrong later on, like either experimentally or even in the future mathematics. For yeah, like he has also, I guess he I don't exactly remember, but I also guess he has a Guinness book for producing the most number of wrong equations in the history of physics or something like that. And if some of his works are even so groundbreakingly wrong that like we it has been marked as yeah, whatever happens, that this is not the way that nature wants us to understand her. So like he has been a patient of depression for most of his life, and it is actually a story of not giving up, because uh, when this Unruh Effect was published, William Unruh was already into almost 25 years of his research career, and he had produced like a chain of wrong researches, but still he didn't give up and continued to work for uh, getting something good going. And this is it. Like it is one of the most pivotal theories of quantum. It is one of the most pivotal expressions, if I may put it like that way, of quantum field theory. And yeah, like this is a story of not giving up. Like the way he continued even when things are not very bright for him. So yeah, getting back from the story, what is Unruh Effect? The Unruh Effect is a kinematic prediction of quantum field theory that an accelerating observer will observe a thermal bath like black body radiation, sometimes even some thermodynamic effects like entropy increasing, or one thing that I should note here, that increase of entropy, though it's almost constrained of fundamental principle of physics, it's not as well established in quantum mechanics as it is in classical or relativistic physics. So yeah, that's the thing to note. And why does an inertial observer would observe now? In a layman's word, it has been shown theoretically. It has not been quite that much experimentally shown, but okay, we will come to that later. So theoretically, that a waved thermometer in empty space with no other contribution of thermal nature will record a non-zero temperature just due to its acceleration. The background appears to be warm for an accelerating reference frame even without any actual thermal contribution, which heuristically we take, we put an uniformly accelerating observer to be seeing an inertial observer in its ground state in a mixed thermodynamic equilibrium with a non-zero temperature bar. Now, I should elucidate a bit on what is this mixed thermodynamic equilibrium. It is also a quantum mechanical concept. Thermodynamics in classical physics deals with only force, only the force like strong nuclear forces and weak nuclear forces, which generate some kind of heat, or which is the direct precursor of heat energy, if I may put it like that way. But quantum mechanics showed us, using its principle of equivalent uncertainty, as proposed by Klein and Gordon in 1927 or 28, that thermodynamical principles in quantum mechanics is not necessarily constrained to the fields of entropy and enthalpy and progenies precursoring it, but it is a mixture of all the four fundamental forces acting in their own fields. So basically, this mixed thermodynamic equilibrium means that it is not only in thermal equilibrium, it is also in a mechanical, it is also in a nuclear, and it is also in an electromagnetic equilibrium. And basically explaining for this effect, then we can say that if a reference frame is accelerating with some inertial, or if I may, for now we can consider it to be at rest, to be with reference to a rest frame, then we will see that the accelerating reference frame will observe some non-zero temperature in the rest frame, even if it is in empty space, just due to its acceleration, if I may put it like that way. So yeah, now getting back on the background a bit, like what is quantum field theory? So basically it's a theory that asks the old Aristotelian question, what the hell are we made up of, with an interesting modern twist of unifying special relativity, classical field theory, and quantum mechanics. As a result of which we got an interesting digression from periodic tables and a foray into modern physics like no other. Yes, in fact, this the thing is, on the top you see the periodic table, as it is not made as a periodic table, but if QFT were to prescribe a periodic table, it would have looked like this, and it without any doubt looks a lot better than the periodic tables of chemistry, and you don't have to remember anything for it, like the electronegativities that increases from left to right and bottom to top, and things like that. It's just these 12 are all equal things, and they are the most fundamental 12 fields that exist in nature. So yeah, it looks a lot better. Uh, QFT is a theory that basically proposes particles as quantized energy excitations of some smooth fields for quantum fields, which, contrary to the basic proposition of quantum mechanics, is more fundamental in this framework. It basically propounds the idea that there are a finite number of quantum fields, 12 till date discovered, that lies inherently in nature, and accelerating frames show quantized energy being propelled as particles from this field, and interactions between particles are described by interaction terms in the Lagrangian involving the corresponding quantum fields. So basically, it means that when we are in a rest frame, we will observe no particles because the quantum fields are all at in an are all in a non-part-up state. The quantum fields are not being disturbed. But when we are accelerating with reference to a field, the acceleration produces an effect known as the particle effect or quantum field effect, which basically excites the field into a quantized form of energies, which we are calling particles in this framework. And this shows a kind of inherent frequency perturbations that almost has the same dynamics and mechanics of Lagrangian mechanics. Like if two particles are dealt with in quantum mechanics, we will often write their Hamiltonian, the Lagrangians, and therefore try to solve out their trajectories and the way they behave. These excitations of energies of quantum fields with only a certain depletion of that it's in some fourth dimensional space. It is more or less the same Lagrangian mechanics that governs this quantum field theory. And QFT has wide range of applications, including in particle physics to construct physical models of subatomic particles, and in condensed matter physics to construct models of quasi-particles. QFT has also gifted us with the nearest thing to theory of everything that we have gotten to, and that is the equation that you can see at the bottom of this slide. There are parts of this equation which nobody on the planet understands, that generally deals with this dark matter and dark energy stuffs, which is not describable by quantum field theory much. And but more or less this equation can predict each and every observation we have made till date in physics labs with the light of these four fundamental forces, and even the dark forces or dark energy which are known till date. So yeah, this is the closest to the theory of everything that physics has taken us, thanks to QFT. So QFT is a very well-rounded theory for that. It's not like string theory or loop quantum gravity, which doesn't have much experimental basis to prove. So what are the things that lets us accept a new framework in theoretical physics? So there are three conditions, three stages of doing it. So the first is that it must explain all the observations that past frameworks did. Like QFT did explain, in fact, all the observations that special relativity and quantum mechanics, old quantum mechanics and new quantum mechanics did. And therefore, the first condition of well-roundedness is satisfied by QFT. It must make some predictions that the past frameworks didn't. Like, for example, QFT had this Higgs field prediction, which Peter Higgs and then also Stephen Fulling did it in around 1965 or 1970. During that time, the Unruh effect is an original prediction of QFT. It can only come if the propositions of QFT are taken into account. So basically, QFT has some pretty good original predictions that the past theories of physics didn't predict, and it must have some experimental verifiability. And yes, QFT did predict about Higgs field, and it has been experimentally verified in 2012 in the Large Hadron Collider operated by CERN. It has also observed the Planck temperature effect. It's a kind of effect of quantum perturbation which tells us that certain temperatures, like for example, like there is an equation that Planck proposed observing some experiments which any theory before QFT didn't could not explain what that equation meant, and that equation was actually explained by QFT to show that certain temperatures are not allowed by universe for these fields to coexist and stuffs like that. So that explained a lot of stuffs, and in fact some observations of black holes that we made for the last 20 years, that why the some black holes have event horizon, some black holes doesn't have event horizon and things like that. So yeah. So now getting back to Unruh effect, what the general expression for Unruh effect is to calculate the temperature that an accelerating observer would see with reference to an inertial observer with respect to a field, and that is basically defined as the effective temperature experienced by an uniformly accelerating detector in a vacuum field. And this vacuum thing is not exactly uh, like this vacuum, like like what can I say? Like this vacuum thing is not exactly empty space in quantum field theory. Like the concept of vacuum is not the same as empty space as it is in quantum mechanics of special relativity. Space is filled with quantized fields that make up the universe as per QFT. Vacuum is simply the lowest possible energy states of these fields. For that, it does have some other conditions, but more or less for this talk, the vacuum is simply the lowest possible energy state of these fields. The ground state, if I may put it like that way, in uh, knowable quantum mechanics. So, in the light of the equivalence principle, that is general relativity, that is one of the greatest triumph of Unruh effect. That Unruh effect is the first thing in a series of discoveries in quantum field theory that has started to kind of coalesce general relativity and quantum field theory. And if we can do that before dark theory, we have a theory of everything. We haven't completely done that. Physicists in Cambridge University and Massachusetts Institute of Technology are working heavily on that. But more or less, this thing, like this Unruh effect, is the first in a chain of discoveries that has started making some some types of bridge and uh, some types of chambers between these two theories, getting into a theory of everything. And uh, it in fact, why I am saying that, it has the same exact same form as Hawking temperature. And as you can see, the expressions for Unruh temperature is on the leftmost picture at the bottom of the slide. That is T is equal to h cut a by 2 pi ckb, where h cut is the reduced Planck constant, a is the acceleration of the accelerating frame or the detector, c is the speed of light, and kb is Boltzmann constant. Uh, the Hawking temperature, that is the temperature that is experienced by a black hole uh, at a certain point of its radiating neutrinos and photons into its event horizon, is given by h cut g by 2 pi ckb, where g is the surface gravity of the black hole, and it is exactly the same form. And in fact, we can even equate that and simplify that to get the equation of this total. This a is basically denoted as the surface acceleration of black hole, and uh, the Unruh temperature and Hawking temperature are actually the same for the black holes. It has been mathematically shown by physicist David Tong. He is a very famous quantum field theorist and is a professor in Cambridge University. And that expression is given by 2 pi AP T by TP, where AP is the Planck acceleration, or acceleration that is defined as a kind of reference to the quantum fields. Like for example, AP or TP is the Planck temperature for that case. For example, if we consider a black hole that has been formed just during the origin of the universe, like just during the Big Bang, and we and at 2022 we term its Planck. We term its acceleration as the Planck acceleration. The surface gravity, uh, the surface gravity, gravitational acceleration of the black hole as AP, and that surface gravitational temperature as TP. Then this form actually comes from the works of David Tong. So yeah. Now, what Unruh effect actually tells us, and what actually lets us deal with Unruh effect. So, getting back to that, we can, for that we have to first define a concept which is called the warm gas concept. What is a warm gas in quantum field theory? So basically, a warm gas is a bosonic gas. Bosonic gas means the particles of the gas that constitutes the gas obey the Bose-Einstein statistics. That is, like it doesn't obey the Pauli exclusion principle, if I may put it like that way. And it has a non-zero critical temperature, a temperature where all the bosons will stand still and have no fluctuatory perturbations. That is how we define a warm gas, like it is a bosonic gas and it will have a non-zero critical temperature. The Unruh demonstrated theoretically that the notion of the vacuum depends on the path of the observer through space-time. From the viewpoint of the accelerating observer, the vacuum of the inertial observer will look like a state containing many particles in thermal equilibrium, warm gas. The Unruh effect would only appear to an accelerating observer. And although the Unruh effect would initially be perceived as counterintuitive, it makes sense if the word vacuum is interpreted in the following specific way that I said. An accelerating observer will perceive an apparent event horizon form. Now, what is an event horizon? Event horizon is defined in quantum field theory as the area of the field that the black hole experiences, not necessarily black hole, any cosmic body experiences, which has an immediate effect of any change occurring in the mother body. Like there will be very like tending to zero time gap within that information relay. And for that, the existence of Unruh radiation could be linked to this apparent event horizon, putting it in the same conceptual framework as Hawking radiation. On the other hand, the theory of the Unruh effect explains that the definition of what constitutes a particle depend on the state of the motion of the observer. Now, these energy states of it is worth noting here that these energy states of any quantized fields are defined by the Hamiltonian, which is basically the total energy of the system, like the total energy of the system of the event horizon, and it can be based on local conditions too, including the time coordinate, because as per special relativity there is a concept of local time that tells us that the way a clock moves in a locality may change from one point in space-time to another point in space-time. And two observers moving relative to each other must use different time coordinates, if I may put it like that way. And if those observers are accelerating, there even may not be any shared coordinate system. Hence, the observers will see different quantum states and thus different vacua in this case. And that is one of the things to note here, like the vacuum in quantum mechanics and special relativity itself is same, is for the inertial observers and the accelerating observers, but not in the case of quantum field theory, and for that the Unruh effect. So the free field here needs to be decomposed into positive and negative frequency components before defining the creation and annihilation operators. These are it's a bit technical thing. Creation and annihilation operators are nothing but like they are the operators which gives us information. Like if we have the information about about a ground state or an excited state of an event horizon system, this creation and annihilation operators operating on the information of those systems will give us the information of other states of that system. So basically that's it. Why they needs to be decomposed into positive and negative frequency, it is because for it has a very good analog, if I may put it like that way, in special relativity. Say there are three frames accelerating at the same time, and one frame is at rest, or say maybe moving at a constant acceleration, some is moving at an hyperbolic acceleration, and some is moving at say a parabolic acceleration. Now the each parameter of parabola, which the eccentricity parameter, if I may put it like that way, it's called the eccentricity parameter. The eccentricity parameter of that parabolic coordinate or the hyperbolic coordinate, they will basically supply us the information of the system as quite decomposed into observations, like the observations, the time like observations that we will see in one frame will be drastically different in other frames, and that's only because they're accelerating in different ways that general relativity tells us. Using the we can actually easily show that effect using Minkowski gravitational metric, and therefore we need to change the time lapse between these frames and connect them through a proper mathematical expression. And for that, as you may understand, that hyperbolic eccentricity parameter, which is in positive, and parabolic eccentricity parameter, which is in negative, must have some proper mathematical expressions connecting them. And therefore, the time lapse or the inverse of that, which is basically the frequency, has to be decomposed into positive and negative components to get a proper mathematical expression. And this can only be done in space-time with the time-like killing vector field. So basically, killing vectors are nothing but vectors in n-dimensional Lorentzian manifolds. A vector space that even you can generalize it to a Minkowski space too. That it is basically nothing but a space that satisfies this Lorentz transformations. And Lorentz transformations are nothing but some linear transformations that arises from special relativity that connects parameters of one informations of one reference frame to the same analogous informations of the other reference frame. And this decomposition happens to be different in Cartesian and regular coordinates. This explains why the particle numbers, which are defined in terms of the creation and annihilation operators in most cases, are different in both coordinates. So the Unruh effect is also expected to be present in d theta space, which is nothing but an n-dimensional spherical, n-dimensional analog of a spherical space, if I may put it like that way. Like it has an d-dimensional volume and d-1 dimensional area, and d theta space is basically like it's a hypothetical space. It hasn't been experimentally verified till date. But d theta space is basically a space which combines the effects of loop quantum gravity, quantum field theory, and general relativity into a single framework of space, time. Yeah, like the Unruh effect, as it has, we will just look at the derivation, kind of derivation of Unruh effect in the upcoming slides. We will see that there is no explicit dependence on frame dependent parameters in deriving the effect. So it is also expected to be present in d theta space. It is also worth stressing that the Unruh effect only says that according to a uniformly accelerated observer, the vacuum state is a thermal state specified by its temperature, and one should resist reading too much into this thermal state or bath. Different thermal states or baths at the same temperature need not to be equal, for they depend on the Hamiltonian describing the system. In particular, the thermal bath seen by accelerated observers in the vacuum state of a quantum field is not the same as the thermal state of the same field at the same temperature according to inertial observers. Furthermore, uniformly accelerated observers static with respect to each other can have different proper accelerations A depending on the separation, which is the direct consequence of relativistic redshift effects. This makes the Unruh temperature spatially inhomogeneous across the uniformly accelerated frames. So this basically says that, to be put in a bit easier terms, that proper accelerations of proper times that are defined with respect to the system as it is moving, moving in the event horizon. It shows the kind of relativistic Doppler effect, a relativistic Doppler effect of thermal nature. But one thing that separates this Doppler effect from the Doppler effect we commonly study or commonly get into use for creating GPSs and military bases and things like that is that they're spatially inhomogeneous. Because as you can see that the temperature depends on the acceleration, and temperature is meant to be a homogeneous parameter, was meant to be a homogeneous parameter, if I put it like that way, before QFT, that if the temperature is not dependent upon frame, but this Unruh effect showed us that this temperature is also dependent upon frame, and therefore this whole effect becomes inhomogeneous in the uniformly accelerated frame. So basically looking at a now we'll look at a simple way to derive the under temperature expression. This is not exactly the derivation which William Unruh did, but this is a pretty good like a pretty this will give us a pretty good idea like what actually is under temperature and how what it means and how it can be derived. Though I should note here that this derivation is not foolproof because this derivation lets us consider certain parameters to be super deterministic, which is in inherent opposition to the common uncertainty principle of quantum mechanics, and therefore this should not be treated as a biblical uh, derivation, but it will give us a pretty good idea about what the thing is dealing with. So, for deriving that, let us first consider an observer moving with an uniform proper acceleration through Minkowski spacetime. Minkowski spacetime is nothing but a common spacetime that is like described by T, X, Y, Z in order, and T is the time parameter, X, Y, Z are the space parameters, and uniform proper. We are considering a uniform acceleration because that will give us the expression of the temperature for the ease of calculations, and uh, we are taking the linear coordinates for certain ease of calculations, and I am giving you the exact relations between the Cartesian coordinates, and yeah, we can actually take the acceleration to be only along the x-axis so that this inhomogeneity of space wouldn't matter to us much, like the y and z axis we need not to worry about that. And the relation between the Rindler coordinate and the Cartesian coordinate is that x, which is the space coordinate in Cartesian system, is equal to rho cos x sigma, and t is equal to rho sin h sigma, where cos and sin are the hyperbolic cos functions and hyperbolic sine functions, and rho and sigma are parameters of the Rindler coordinates. Rindler coordinates are used to describe the Rindler space, which are nothing but accelerations which occur in an hyperbolic way, like accelerations where the space-time elemental form is given by this ds2 is equal to minus rho square d sigma square plus d rho square. This like if in any space the acceleration satisfies this elemental coordinate relation, then we call that space a Rindler space, and it is described with these parameters rho and sigma, which are the Rindler coordinates. So an observer moving with fixed rho traces out a hyperbola in Minkowski space. Therefore, this type of motion is called hyperbolic motion. The coordinate rho is related to the Schwarzschild spherical coordinate r by relation of figure 3. Yeah, I need to explain this a bit. The Schwarzschild radius is a concept of general relativity. We are actually why this was a triumph of Unruh effect, that it could coalesces some of the effects of QFT with general relativity, which is not usually covered in QFT, and that basically supplies us with the expression of rho is equal to integral rs to r dr prime root over of 1 minus rs by r prime, where this is basically the Schwarzschild relation, which relates the, like if we do, like if we have an event horizon and we have ample information about that event horizon and we solve for its rho and sigma, we are considering that it's situated in a Rindler space, the event horizon is situated in a Rindler space, and if we do solve for this rho and sigma, it will supply us with the values of it will supply us the values of the radius of that event horizon, uh, the area of effect, if I may put it like that way, of that event horizon. This rs is the minimum amount of distance that an observer should be from the mother body of that event horizon to observe its effect, and r is the maximum distance where this Schwarzschild it is called the Schwarzschild radius. The event horizon's effect can be seen without with an immediacy of time. So yeah, that's it. And now we consider that an observer moving along a path of constant rho is uniformly accelerating and is coupled to field modes which have a definite steady frequency as a function of sigma. Now, what does this mean? it means that do you guys do you guys know these particle in a box equations like yeah, but I guess we all studied it in first semester because I guess we are all from in ICS. Yes, so yeah, I will refer this to I will refer that to explain this. So basically, when for example we are dealing with a particle in a box, we have often seen that we carve down the boundary conditions into a smooth Dirac delta potential, but that doesn't necessarily occur in nature. But for that, it is also a kind of like this approximation we are assuming here is also a kind of approximation in the likes of Dirac delta potential. For example, uh, say we have a constant rho and we have an observer who is uniformly accelerating in that Rindler space, then we are uh, we are claiming or we are demanding that the quantum fields that the observer passes through in that Rindler coordinate or that Rindler space-time are coupled to certain excited states called the field modes of the quantum fields, which have a steady frequency as a function of sigma, which have a constant frequency. Steady frequency means a slightly different thing in QFT, but that doesn't matter much in this derivation. So we can consider steady frequency as constant frequency in this case, and we consider that to be a function of sigma to get the yeah, like it can be a function of rho too, but since rho is a constant we can just explicitly multiply it out and nothing else. So these modes are constantly Doppler shifted relative to the ordinary Minkowski time as the detector accelerates, and they change in frequency by enormous factors even only after a short proper time. That one of the problems that Unruh effect cannot be experimentally verified very quickly is the fact that ordinary like these modes are of course Doppler shifted. There are relativistic effects, so there will be relativistic Doppler effects, and these Doppler effects tend to be very large in number, humongous in magnitude, even within a short proper time in the Minkowski space-time. And since QFT does deal with like even d theta space is also just a generalization of the Minkowski space-time. So basically, the conditions of the Minkowski space-time holds in even this Doppler effect. So even in these Doppler shifted effects, so this there are like humongous change in ways of there are humongous change in ways of observing these sequence, if I may put it like that. So translation in sigma is a symmetry of Minkowski space. It can be shown that I am not going into that calculation. It is a pretty humdrum calculation and it requires some suppositions of gauge theories, and that is a pretty high mathematics. Even I don't know that. So I'm just using the result here that it can be shown that it corresponds to a boost in xt coordinate around the origin. So basically, if we change sigma to sigma plus d sigma, then it can be shown that it basically corresponds to a change of x plus dx and t plus dt. We must note here that it is only plus. We are not dealing with decelerations here. Deceleration will bring an additional minus sign to the Rindler metric, which will be pretty hard to get rid of. So we'll always be dealing with the reference frames, which we will consider as stationary. So the boost will be x plus dx and t plus dt. Any time translation in quantum mechanics is generated by the Hamiltonian operator. It is a well-known result of quantum mechanics. So for a detector coupled to modes with a definite frequency in sigma, we can treat sigma as time, and the boost operator is then the corresponding Hamiltonian. In Euclidean field theory, like for just generalizing it, but the minus sign is in front of the time of the Rindler metric, is changed to a plus sign by multiplying I to the Rindler time. The Rindler metric is turned into a polar coordinate like metric. Therefore, any rotations must close themselves after 2 pi in an Euclidean metric to avoid being singular. So basically, what we are demanding here, that when we are generalizing that Minkowski space-time to a Euclidean space is basically the day-to-day 3D space, nothing else. The Rindler metric is basically a system that determines that the proper distance between two event horizons, if I may put it like that way, two event horizons between in the Minkowski space-time, and that Rindler metric is nothing but a way of measuring that distance, and it is not like that. It's not a way. It is I may put it like that. It is a scale. It is a polar coordinate like scale that determines this distance, and as I said, that there will be a minus sign, and that minus sign will be pretty hard to get rid of. So we are mathematically dealing with it. We are just multiplying the imaginary factor I and getting the metric into a 4x4 matrix form, and that being that the rotations okay, let me introduce you to a concept here. It is called the quantum benefice. It basically shows us that any type of symmetric event that is occurring in quantum mechanical space, that is often called the Bell space or Hilbert space. Hilbert space is a bit more specialized one. Let us go to Bell space. Uh, it tells us that those symmetries are almost always contained within a 2 pi phase. That is, in mathematical terms, e to the power I 2 pi phi, where phi is the coordinate that describes as the symmetry of that event horizon, is always 1. So this basically, the Rindler matrix basically becomes analogous to the 4x4 Pauli matrix, and that Pauli matrix can be that Pauli matrix can be generalized into the Euclidean metric, and by the result of Euclidean geometry, it can easily be claimed that these rotations must close themselves after 2 pi. It can even be claimed from quantum mechanics itself, like from the basic propositions of Hilbert space. There is nothing fancy. But now there is something fancy, because we are introducing a concept here which is known as the weak rotation, and weak rotation is basically like weak rotation is do you guys do you guys know about how the Ehrenfest theorem and things stuff like that defines how a symmetry works in Hilbert space? Or should I explain that too? Hello. Hello. Can you hear me?
Can you repeat what you said just now? Something I did not get it.
Yeah, I just said that should can I assume that everybody knows how these things work in like how the symmetry operations work in Hilbert space and Bell space, like those uh, quantum mechanical spaces, and can I assume that and explain weak rotation with that? Okay, I am explaining. Basically, Ehrenfest theorem relates a kind of symmetry to basically Ehrenfest theorem tells us that any kind of symmetry leads to a conservation of some kind, a conservation of any physical stance or physical parameter. So uh, mm, with that being said, like we have just supposed that there will be a 2 pi phase difference in the Euclidean metric. There is a method of solving such equations like e to the power I 2 pi phi is equal to 1 for phi. That is a method of the weak rotation. It is a kind of differential equation. It generates a kind of differential equation which helps us in finding the real time coordinate, and uh, that is given by this beta. Like we are taking the inverse of the temperature here. Like yeah, okay. I am using a convention here which is not used in QFT generally, but I am using here just for some ease of calculation, that I am taking the inverse of temperature as a parameter while dealing with the calculations in these stances, and that thing uh, I call it beta. I denote it by beta, and it is nothing but just the inverse of temperature. And therefore basically this periodicity that this real-time coordinate will face is almost analogous or dual to a thermal partition function. The probability that relates this bosonic gas to its distribution, it will have a periodicity, and that periodicity is will be equal to the imaginary time that will correspond to a temperature of like, how can I say it like that? Like this periodicity in a completely mathematical sense will denote the imaginary time, the imaginary unit of the proper time that comes from that e to the power I 2 pi phi is equal to 1, that phi. And in the real world, when we are translating it that into Hilbert space or Bell space, that imaginary time corresponds to the temperature, where beta is related to the temperature as 1 by T in thermal Q. So basically, this is not an actual temperature because Hamiltonian is dimensionless, and for generation of that time translation, it has to be back to that actual temperature, but it is conjugate to the time-like polar angle sigma, which is also dimensionless. To restore the length dimension, it is to be noted that a mode of fixed frequency f in sigma at position rho has a frequency which is determined by the square root of the absolute value of the metric at rho, the redshift factor. Basically, we are just restoring the unit here to get the equation. We are just claiming that a mode of fixed frequency f in sigma at position rho has a frequency which is like, if we determine the value of the Rindler metric at rho, we are defining it for a constant rho, and we find the absolute value of it. It is just the square root of it, and that is also the Doppler redshift factor for these frequency modes. So yeah, and this can be seen by transforming the time coordinate of a Rindler observer at a fixed rho to an inertial co-moving observer observing in a proper time. So yeah, the general relativistic principle of equivalence holds here. With the Rindler line element given above, this is just true. Therefore, the actual thermal inverse temperature at this point is given by the expression in figure 4. That is beta is equal to 2 pi. It can be shown that the acceleration of a trajectory at constant rho in Rindler coordinates is equal to 1 by rho. So basically, that expression reduces, that connects beta with the acceleration as beta is equal to 2 pi by a. And restoring the unit, like putting c back and Boltzmann constant back and getting the length dimension back for from the frequency mode, will generate the expression of the Unruh temperature, that is T is equal to h cut a 2 pi ckb, and that's it. Like beta is equal to 2 pi a is basically the Unruh temperature in C is equal to 1 and Planck units, nothing else. And basically restoring the units will get us to the familiar expression of Unruh temperature. And as I told that this derivation is quite a brief lookup. Like this is not the actual derivation which Unruh did, but it does give us a pretty good idea of what Unruh did in terms of QF. So the temperature of the vacuum seen by an isolated observer accelerating at the Earth's gravitational acceleration of g is equal to 9.81 meter per second square is only about 4 into 10 to the power minus 20 Kelvin. For an experimental test of the Unruh effect, it is planned to use an acceleration up to 10 to the power 26 meter per second square, which would give a temperature of about 0.4 million Kelvin, because that much is required to sense the collisions that happens at LHC in CERN. Of course, all the experiments of this sorts are done in LHC in Switzerland, as operated by CERN. And of course we can't our technology is still not that much advanced enough. We have some processes like adiabatic demagnetization or adiabatic de-electrification, which can sense temperature up to 10 to the power minus 10 Kelvin, but 10 to the power minus 20 Kelvin is a pretty much out of the way temperature to us with current technology. So basically for that we will use tau neutrinos. Tau neutrinos are obeys Bose-Einstein statistics. So the gases of tau neutrino are generally the gases of tau neutrinos are generally bosonic gases. We will use tau neutrinos. It is being planned to use in tau neutrinos. In fact, a Bengali scientist is in charge of this experiment. Professor Otonu Moulik, he is a professor in University of Bologna, and mm, we are like the LHC is almost planning to use 10 to the power 26 meter per second square of acceleration using these tiny neutrinos colliding into each other. That will give us a temperature of about 0.4 million Kelvin. Uh, I guess we can observe that, but yeah, we'll get back to that a little bit later. So first, let us look at the aftermath of Unruh effect, like what the Unruh effect tells us about, like what are the effect, like what Unruh effect predicts us about the future of QFT, if I may put it like that. So the Unruh effect would cause the decay rate of accelerating particles to differ from the inertial particles. Stable particles like the electron could have non-zero transition states to higher mass states when accelerating at a higher enough, like for example. So basically the like decay rate, a decay phenomena almost as simple as radioactivity, that may also change from Unruh effect. Like if the radioactivity we are counting, there are many counters available. There's the Sokolov counter, the Geiger-Müller counter. These counters will count different number of counting phenomena that's occurring in the inertial frame than in the accelerating frames, and they can have even non-zero transition states, like the Balmer line, that is the Rydberg constant. The Rydberg constant will change from one frame to another, and that is quite a pretty new discovery, because alongside temperature, one of the other things that we did consider constant in para theories to QFT in every frame is the number of counting phenomena, like number of particles, number of electrons emitted from radioactive decay. But Unruh effect tells us that even that is not constant. So although Unruh's prediction that an accelerating detector would see a thermal bath is not controversial, the interpretation of the transitions in the detector in the non-accelerating frame is. It is widely, although not universally, believed that each transition in the detector is accompanied by the emission of a particle, generally a photon, because I am coming to that as the Sokolov-Tarnoff effect. I will tell that why this particle is photon, and that. But let us now for consider that it can be any particle, and that this particle will propagate to infinity and be seen as Unruh radiation. The existence of Unruh radiation is not universally accepted. The skeptic scientists accept that an accelerating object thermalizes at Unruh temperature. They do not believe that this leads to the emissions of photons, arguing that the emission and absorption rates of the accelerating particle are balanced. Uh, yeah, no, yeah. So now I will briefly describe about the experimental things, like the experimental trials that have been to observe the Unruh effect. Uh, as it is with many new theories that has been proposed after 1970, it has unfortunately not been verified. It has been seen like there have been some claims of observing Unruh radiation, but there may have been other sources of that radiation too. So we are not exactly undoubtedly sure that this is Unruh radiation. So we cannot be undoubtedly sure that Unruh effect exists in real life. However, there are several claims. So basically, it has been claimed that the experiments that successfully detected the Sokolov-Tarnoff effect may also detect the Unruh effect under certain conditions. It will make use of the electrons as a thermometer and will collide them in the LHC to produce the effect. So basically, the Sokolov-Tarnoff effect, I am elucidating on that a bit. It is also a effect of quantum field theory. It tells us that electrons, when not necessarily electrons, fermions, the particles which obey the Fermi-Dirac distribution or Fermi-Dirac statistics, uh, does have a kind of uh, a way, if I may put it like that way, a way of relaying information to each other, that if an electron, say for example, we are considering an event horizon of a group of electrons, and that event horizon is spread from minus r to plus r, and at minus r, an electron suddenly jumps up to a height of say 1 meter. Sokolov-Tarnoff effects says that through the phenomena of self-polarization, the electron situated at plus r of the event horizon will also have a kind of reciprocal effect, like it will move downwards for 1 meter. And we, like, this has been shown, like this has been experimentally verified that this effect is actually there. So basically we will use this effect to detect the Unruh effect, like how when two electrons, if one electron is going up and another electron is going down, then the Pauli exclusion principle, which is applicable for the fermions, states to us that certain parameters of the electrons, certain inherent parameters, including spin, must be different. Therefore, when they are fused together, when they will be within the local event horizon of themselves, they will annihilate each other. The annihilation operation suggests to us that these polarizations will annihilate each other, and therefore must generate some form of electromagnetic radiation. And these radiations are mathematically shown by Professor. um his name is he's an Italian physicist and considered the father of physics. Yeah, Professor Carlo Rovelli. It has been shown by Carlo Rovelli that in 99.99% of the cases, this electromagnetic radiation will be gamma radiation, and the gamma radiation is basically the photons. So yeah, the Unruh effect, like, so basically the Unruh radiation I told about, the particles that will be emitted for the Unruh radiation, is nothing but the electrons. It's nothing but the what can I say? Is nothing. Uh, it will make, yeah. So of course, if it is using the electrons as a thermometer, it must generate photons as the it must generate photons as the medium of that Unruh radiation. So yeah, it will be very easy to detect for the LHC because LHC has pretty powerful photon detectors. Theoretical work in 2011 using quantum verifiers suggests that accelerating detectors could be used for the direct detection of the Unruh effect with current technology. They showed that a detector acquires a Bery phase due to its motion in space-time. The phase is different in the inertial and accelerated case as a direct consequence of the Unruh effect. And that is also a very easy thing to observe because Bery phase is a pretty like large scale observation. It is a pretty large scale perturbation in space-time. So yeah, it can also be very easily detected. So concluding my presentation, I can say that Unruh effect is actually a very important pillar in proving the inevitability of QFT as the theory of everything. because it is the first connecting bridge of QFT to general relativity through the form of Hawking radiation of Schwarzschild black holes. If we are able to connect QFT with here, we are basically done with the University of Physics up to dark energy, because uh, we are still not like nobody on the planet still knows what the hell is dark energy. So up to dark energy we have unified physics. We have to unify dark energy with it. Unruh Effect is also a story of motivation for not giving up as to all the budding physics students, showing that a lifelong of failures and embarrassments, if not culminated, is the only stepping stone to a purposeful career in research and finding meaning in life through the path of the universe. And researchers from the whole world are now looking forward to CERN operating on the LHC to give us a final experimental result of the observation of Unruh Effect. And this is basically a picture that has been published in uh, uh, that has been that was published in the 2011 paper that showed that the junction of the LHC that was dedicated to accelerating the electrons produced in the tau neutrino experiments that were later used to detect the Sokolov-Tarnov effect, and hence shown by the 2011 framework and used to detect the Unruh effect too. So yeah, with that I uh, conclude my presentation, and these are some of the papers and books that I cited while creating this presentation. I have been reading quantum field theory for some time, and therefore uh, I have been reading this book called Quantum Field Theory by David Tong, which has been published by the Cambridge University Press, and this is a fantastic book for any physics students, not for any physics students only, for any students who are into the philosophy of science. This is a must read, because this book lets us deal and lets us uh, feel the essence of physics in ways that are like um, you know, that lets us seize the Aristotelian philosophy into the light of modern science, and hence lets us think in the way of formal logic, and the ways of looking at universe is more polished into this. So yeah, you like, if you are into the philosophy of science, you must read this book called Quantum Field Theory. But yeah, and if you are interested in quantum field theory but not as much into the technicalities of physics, like into the gauge theories or symmetry transformations or Lie algebras or stuff like that, you can actually consult a book called the like Quantum Field Theory for Gifted Amateurs. Uh, it has been written by one second. It has been written by the Finnish physicists Stephen Blundell and Tom Lancaster. It does not delve into the technicalities of quantum field theories much, but will give you a very good idea of what the theory deals with. If you are through with some basic physics knowledge and stuff like that, these are some of the other papers. Which this slide will be available in the UGO webinar website. Um, so if anybody wants to cite these papers and books for further delving into the topic, they will find the papers and books there. And if anybody wants to talk with me on this topic more, and like just talk about the philosophy of it, you are welcome to talk. I'll be glad to talk with you. And with that, I conclude my presentation. Thank you.